Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Have you ever wondered how money loses value, how your investments grow, or why some chemical compounds vanish over time? Well, in today's video, we're going to walk through all of that using exponentials and logs. So let's start with the basic exponential model. And you might recognize this because we briefly mentioned it in our intro video. So the exponential model says that P of t is equal to P0, also called P0, multiplied by 1 plus r to the power of t. This is the foundational model used in almost all exponential problems. So P of t here is the amount of whatever we're looking at time t. And that could be amount of money, that could be amount of some radioactive isotope. And the P0, or P0, is the amount that we started with. So what this means is at time 0, meaning P of 0, that is going to be P0 multiplied by 1 plus r to the power of 0. And that is going to be equal to just P0. Now, P of 1 is going to be P0 multiplied by 1 plus r to the power of 1. And now P of 2 is going to be P0 multiplied by 1 plus r to the power of 2. So notice how here we have a geometric pattern. As we increase our t value, we're multiplying by this constant factor of 1 plus r. So now let's go ahead and take a look at a real-life example. So using data from Canada Food CPI, we want to create a model that illustrates food price increase over the last couple of decades. And we're going to be using the data from the year 2002 to the year 2024. So CPI stands for Consumer Price Index. So in 2002, the index was set at 100. So what that means is the average price of, say, a basket of goods was $100. And then by 2024, that same basket of goods has risen to an index of 189.3, meaning for that exact same basket of goods, it now costs you $189.30 instead of that original $100. So over the 22 years, the average has almost doubled. So let's go ahead and use that exponential model that we saw earlier to determine at what average rate the CPI has been increasing by each year. So we start with P of t is equal to P0 multiplied by 1 plus r to the power of t. Our t here is not going to be the year number. It's going to be the number of years that have passed since 2002, because that is our starting point. So now we know that P0 is going to be equal to 100. And then we know that P of t is equal to 189.3, where t is equal to 22. And now we can go ahead and substitute these numbers into the equation. So we're going to get 189.3 is equal to 100 multiplied by 1 plus r to the power of 22. We're going to divide both sides by 100, and we're going to get 1.893 is equal to 1 plus r to the power of 22. We're going to take the 22nd root of both sides. So then we get 1 plus r is equal to the 22nd root of 1.893, and then r is equal to that 22nd root minus 1. And then you're going to need a calculator for this, and you're going to get r is roughly 0.029. So converting that to a percentage, we're going to get that on average, the CPI has been increasing by 2.9% per year. So now the question is, if this trend were to continue, what will the index be in 10 more years? So in 10 more years, that tells us t is going to be equal to 32. Our p naught is still 100, and we're looking for what p of 32 is going to be. So let's go ahead and put that into our equation. So we're going to get p of 32 is equal to our p naught, which is 100, multiplied by 1 plus 0.029 to the power of 32. So here I've written down 0.029, but make sure that when you're putting this into your calculator, you're using the full decimal, because a rounding here could actually change your final answer by quite a large amount. So if you use your answer button from what you got in the previous question, you should end up with this is equal to roughly 253. So a CPI of 253 in 10 more years tells us that, on average, the basket of goods and services that used to cost 100 in the base year, which is 2002, is actually going to cost 253 in 2034. And that is a terrible sign for consumers because it tells us how a dollar loses buying power over time, and why exponential models are essential for understanding inflation. So for our next example, we're going to take a look at something a little less depressing, and maybe a way for us to combat that inflation. So suppose we are to invest $5,000 into an investment that earns us 6% annual interest. And this 6% annual interest can be compounded in different ways. So it can either get compounded annually, semi-annually, or monthly. And we want to figure out how much would the investment be worth in all three ways after 10 years. So you can think of compounding as how often the interest actually gets paid out to you. If you're earning 6% interest and it's compounded annually, then you earn that interest after every year. And once the interest goes into your bank account, that interest starts earning interest. So if you have an account with interest that compounds monthly, then that means the interest gets paid to you every month and it starts earning interest sooner. But note that this 6% is per year, not per compounding period. So if you have an account that compounds semi-annually, you're not getting 6% every half a year. You're getting 3% every half a year. So 3% every half year means in total you get 6% per year. So let's go ahead and take a look at the annually scenario first. So this one is annually. So the T here is the number of compounding periods. And because it compounds annually, then that means in 10 years, we're going to have 10 compounding periods. So we're looking for the amount of the investment after 10 compounding periods. So that is equal to the amount that we started with, which is 5,000, multiply by 1 plus, and the rate is 0.06. And we're going to raise that to the power of 10 for the 10 compounding periods. And if you put that into your calculator, you're going to get this is roughly $8,954.24. Now the next scenario, the investment pays you 6% annual interest, but it's compounded semi-annually. So what that means is that we're going to get 20 compounding periods because we have a total of 10 years. It compounds twice a year. So in total, we get 20. So then we are going to get P of 20 is equal to 5,000 multiplied by 1 plus. And remember I said that you don't get the 6% every half year. You would get half of that 6%. So 0.06 divided by 2. And this is to the power of 20. Putting that into a calculator is going to give us roughly $9,030.56. And now the last scenario is that the interest is compounded monthly. So each year there are 12 months. And if this is 10 years, then that means we're going to have a total of 120 compounding periods. So the value that we're looking for is P of 120. and that is going to be equal to 5,000 multiplied by 1 plus, and now this 6% interest is going to be divided equally into 12 months. And we raise that to the power of 120, and this gives us roughly 9,096.98. So notice how for these three scenarios, our time frame is exactly the same. It's 10 years. But if the compounding happens more often, then we actually end up with more money. And that actually makes sense because if we have more compounding periods, then that means they pay you the interest more often. So you get to start earning interest on interest sooner. For our next example, we're leaving the world of finance and into science. So we have a radioactive sample that has a half-life of 5,730 years. And we want to find the number of years that have passed for it to be at 3% of its original amount. So when we say half-life, that means it takes that many years for the sample to have 50% of what it was originally. So if we let t be number of years, and we let p of t be the percentage of the original sample remaining, let's go ahead and find some value pairs first. And we're also going to write this percentage as a decimal number. So when t is 0, we're going to have the full sample remaining, so it'll be 1. When t is equal to 5,730, then that means half of it is going to be left because that's what the half-life is. So it'll be 0.5. And then in another 5,730 years, so meaning when t is equal to 11,630, we're going to have half of what we had 5,730 years ago. So it'll be 1/4. And then another 5,730 years, that'll be 17190, and then it'll be half of a quarter, so it'll be 0.125, and so on. So using this information, let's go ahead and write down the equation. Okay, so we're going to have p of t is equal to our p naught multiplied by 1 plus, and then our rate here is negative 0.5 because it decreases by 50% every 5,730 years. And then our power here is going to be t divided by 5,730 years, because notice how our value pairs are multiples of 5,730. So now let's go ahead and put in the values that we know. We know that t is the value that we're trying to find. And we know that at that time, there's only 3% of the original amount remaining, meaning p of t is equal to 0.03. And then our p naught is going to be 1, because that was 100% to start with. And this will be times 1 minus 0.5, so that'll be 0.5 to the power of t over 5,730. Taking the natural log of both sides will give us ln of 0.03 is equal to, and we can pull the exponent down, so that'll be t over 5,730 multiplied by ln of 0.5. Isolating t is going to give us t is equal to 5730 times ln of 0.03 divided by ln of 0.5. And then putting that into your calculator gives you, this is roughly 28,987.46 years. So now let's do a quick recap of everything that we covered in this video. We saw how powerful exponential models are. They can be used to explain inflation through the Canadian food CPI, and it showed us how money slowly loses its purchasing power. It is also used to calculate how investments grow and how compounding more frequently changes the final outcome. And it can even be used to model how radioactive materials decay, leading to the half-life formula. So all of these, whether it's growth or decay, are just variations of the same base formula. And now it is your turn to give this a try. Suppose you invest $2,000 into an account that compounds at 4% quarterly, so meaning 4 times a year. But at the same time, inflation is 2.5% per year. So how much money is your investment worth after 15 years? And what will be the real value of your investment, meaning adjusted for inflation, after 15 years? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on applications of exponentials and logs in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.